Friends, this is the lecture number 17. Today we will discuss eigenvalue, eigenvector and diagonalizable. Okay, you must go in the previous lecture to know about this eigenvalue, eigenvector. Again I am just writing. We have written this formula for the eigenvalues. Okay, so this is for lambda cube. Okay, for 3 into 3 matrix. If you want to know about 5 into 5 matrix, then what will you do? Lambda ki power 5, principal minor of order 1, lambda ki power 4, principal minor of order 2, lambda ki power 3, principal minor of order 3, lambda square, then after then similarly. Okay, so this is 3 into 3 matrix. What we have written? Lambda cube, trace of the matrix, lambda square, principal minor of order 2, lambda, principal minor of order 3 is equal to 0. For 2 into 2, here we have just taken this example. So what will you do? Lambda square minus principal minor of order 1, it means that trace, and plus principal minor of order 2, it means that determinant. Okay, for 2 into 2 matrix you will use this formula. Okay, this is the principal minor of order 1, this is the principal minor of order 2. Principal minor of order 1 means you have to take one element who are at diagonal. Diagonal means the matrix you are taking 1 into 1 matrix by the help of diagonal. So this element will come, this element will come. So we have taken this 3 plus 2 means trace of the matrix. Now principal minor of order 2 means you have to take two element. By the help of two element, if you are just taking two element, then you will get corresponding to this, you will get this, corresponding to that, you will get this one. So the whole matrix will come. So means determinant. Okay, so that is the short trick. Lambda square trace plus determinant of the matrix is equal to 0. So we have written lambda square 3 plus 2 lambda plus plus determinant 3 into 2 minus 2 under 2. 6 minus 2 is equal to 0. Lambda square minus 3 plus 5 lambda plus 4 is equal to 0. If you solve it, then you will get this one. Okay, so you got lambda 1 is equal to 1 and lambda 2 is equal to 4. Okay, now the basic formula, this is ax is equal to lambda x to find the eigenvalues and eigenvector. So it will come here a minus lambda into I into x is equal to 0. Okay, so if it will come here, then you will get this one. Now 4 lambda 1 is equal to 1. Now put this matrix here, 3 1 2 2. Okay, then after then minus 1 into 1 0 0 1. Okay, so if you will solve this, x means there are two variable. Okay, is equal to 0 0 0 0. If you will solve it, then what will you get? 3 minus 1, 3 minus 1. Okay, and this is 1 minus 0, 1 minus 0, then you will get 2 minus 0, 2 minus 0, then you will get 2 minus 1, 2 minus 1. Okay, you will get this one. If you will subtract it, two matrices, then you will get x1 x2 is equal to 0 0. Okay, solve it. 3 minus 1 is equal to 2, 1 minus 1, 2 minus 2, and 2 minus 1 is equal to 1. Okay, this x1 x2 is equal to 0 0. Now compare, you will get 2x1 multiply this to this, then you will get 2x1 plus x2 is equal to 0, multiply this and this, then you will get 2x1 plus x2 is equal to 0. So both are same, so you can take any one. So 2x1 is equal to minus x2. Okay, so what is the meaning of this? Now for eigenvector, note it, eigenvalues are unique. Eigenvalues are unique. Okay, but eigenvector, that is not unique. Okay, you can take many values. These are the linearly independent. Okay, so you can take, if you just take x1 is equal to 1, suppose we are taking x2 is equal to 1. For x2 is equal to 1, you will get 2x1 is equal to minus 1. Okay, then x1 is equal to minus 1 upon 2. You will get x1 is equal to minus 1 upon 2. Okay, it's totally depend on you. If you are taking x1 is equal to 1, suppose, okay, this is 1 upon 2 na. So suppose you are just not you are taking another value. Suppose I am taking x1 is equal to 1. It's totally depend on you. Okay, so suppose I am taking x1 is equal to 1, then you will get x2 is equal to 1 into 2, but it minus 2. So this is the eigenvector. This eigenvector 1 and minus 2 4 lambda 1 is equal to 1. This is 4 lambda 1 is equal to 1. This is the eigenvector for lambda 1 is equal to 1. Similarly, you will find the eigenvector for lambda 2 is equal to 4. Now we are finding for 2. Again we will put the same thing. Ax is equal to lambda x, then a minus lambda into I, x is equal to 0. Now a means 3 1 2 2, okay, then minus lambda is equal to, you are taking 4, then this is 1 0 0 1, and after then this x means variable x1 x2, you can take anything, x, you can also write here xy, it's depend on you, okay. So this, now solve it. 3 minus 4 is equal to minus 1, 1 minus 0 is equal to 1, 2 minus 0 is equal to 2, and 2 minus 4 is equal to minus 2, okay. So after then x1 x2 is equal to 0 0. Now compare, multiply this and this, then you will get minus x1 plus x2 is equal to 0. Multiply this and then you will get 2x1 minus 2x2 is equal to 0. So if we'll just it will come here, then after then you will get x2 is equal to x1. So here also it's totally depend on you. I told you that eigenvector means there are maybe infinite eigenvector with respect to lambda 1, but eigenvalue, that is unique. It will be unique, okay, because every polynomial, the solution of any polynomial will be unique. There are only two solutions for such type of polynomial. Lambda square means this is the polynomial. This is the polynomial. X square minus 5x plus 4 is equal to 0. You can write anything. Here I have written lambda. Lambda square minus 5 lambda plus 4 is equal to 0. Okay. So there are only two lambda that will satisfy this equation. But eigenvector that are infinite. It's totally depend on you. Now you can take any value. Suppose I am taking 1. Let x1 is equal to 1. So x2 is equal to x1 is equal to 1. It's totally depend on us. So this is the another vector for lambda 2 is equal to 4. Okay. So this is the eigenvector corresponding to lambda 2 is equal to 4. This is the eigenvector corresponding to lambda 1 is equal to 1. Okay, so we have got two eigenvectors corresponding to two eigenvalues. Okay, so now today we will discuss about that what is the diagonalizable. Okay, we will talk 1 minus 2. Okay, we have got last time 1 minus 2. The first one, this is the eigenvector for lambda 1 is equal to 1. This is the eigenvector for lambda 2 is equal to 4. Okay, so this is the v1 is equal to this, v2 is equal to this. Now a v1 means a is this matrix and v means this. Now multiply this to this. 3 1 3 and 2 1 2. 3 minus 2, multiply this and this, 2 2 4, minus 4. So you will get 3 minus 2 is equal to 1, 2 minus 4 is equal to minus 2. Okay, again you are getting same thing. So you can also write it 1 into v1, because already this is v, 1 into v1. Again we are writing a into v2 is equal to 3 1 2 2, and after then v2 means 1 and 1. So you are getting, multiply this and this, 3 1 ja 3 and 1 1 ja 1, 3 plus 1, multiply this and this, then you will get 2 1 ja 2, 2 1 ja 2. Okay, then you will get 3 plus 1 is equal to 4. Okay, you can also write like this 4 1 1. It means that you can write 4 into v2. Okay, so what we have got, a v1 is equal to, so what we have got, a v1 is equal to, this is lambda 1 v1, and by this we have got a into v2 is equal to lambda 2 into v2. So we have got this equation. Okay, so by the help of this eigenvector we got a matrix, that is, place this here 1 minus 2, place this here 1 1. This is a new matrix by the help of eigenvector. Okay, so by the help of this eigenvector, and if you will find the P inverse, you must know that how to find the P inverse. Just go in the previous lecture, you will know how to find P inverse. So the P inverse is equal to 1 upon 3. I have already calculated. So this is 2 upon 3 and this is 1 upon 3. The shortcut method means this. Suppose you have matrix is this. Okay, A, B, C, D. Okay, replace A and D. A will come here, D will come here, and both is negative. Okay, one will come here, one will come here, and both is negative. Then after then determinant of the matrix. Determinant of the matrix is equal to 3. 1 into 1 minus 1. So okay, P inverse is equal to, you will replace upon 1 upon determinant. This is the A inverse. Okay, if you have A is equal to ABCD, then A inverse is equal to 1 upon determinant of A into replace this one. A will come here, D will come here, and both will be negative. Okay, this is the way to find the determinant of the matrix. Okay, so you have got P and P inverse. So if you will multiply P inverse into A into P inverse, then you will get D. That is the diagonal matrix. Okay, so now P inverse is 1 upon 3, 2 upon 3, and this is minus 1 upon 3 and 1 upon 3. 1 upon 3, 2 upon 3, minus 1 upon 3, 1 upon 3. And multiply to this matrix 3, 1, 2, 2. Then multiply this, this is a P, okay. This is a P, P is here 1, 1, minus 2, 1. If you multiply all 1, then you will get this one, 1, 0, 0, 4, okay. So if you multiply this P inverse, or you can also write PA, P inverse, it's totally depend on you. Then D will come, P inverse AP or PA, P inverse, you will get D, okay. So multiply all, you will get. So you can see that at the diagonal you are getting the eigenvalues. These are lambda 1, 0, 0, lambda 2, okay. So this is the diagonalizable of the matrix, okay. So what is the meaning of diagonalizable? Diagonalizable matrix can be possible if you have distinct eigenvalues. If you have distinct eigenvalues, then the matrix will be diagonalizable, okay. So, but it is not necessary, not sufficient condition. That is the necessary condition, okay. If you have distinct eigenvalues, then definitely the matrix will be diagonalizable, okay. If you have not distinct eigenvalues, maybe the matrix is diagonalizable. So at that time you have to just check, okay. If you will get D, if you will inverse, okay, you have find the eigenvector. By the help of eigenvector you find this matrix and you find this P inverse. If you will multiply this one and you will get a D. D means the all the eigenvalues that is placed here. So you are getting such type of D. It means that the such matrix is called the diagonalizable. So okay, this is the exact definition of diagonalizable and eigenvalues and eigenvector. Okay, just go to the previous lecture, this lecture, listen many times, then your concept it will be clear. Okay, thank you so much.